Welcome to a video on how to model data, i.e. we need to fit curves to our data, and this usually requires either a graphing utility or some advanced statistical software. So we're just going to look at these objectives on how to graph data points in a scatter plot, how to determine what kind of function would best fit it, how to use some sort of graphing utility or program to then create an equation that models that data, and then to graph those data points and the model on the same graph. Okay, so linear regression is the most commonly used form of modeling data. And it's the idea that you have a bunch of data points that you've gathered from real world observations, and now you want to go backwards, right? You want to regress back to fitting a function to it that will model those points. And obviously with linear regression, you're trying to fit a linear model to it. Obviously not all things will fit a linear model well, and oftentimes you'll fit a quadratic equation to it or a logarithmic and all sorts of other things. But in this particular technique, we're trying to find the line, the best line that fits the points that's an actual straight line. And when we're doing linear regression, the whole process of performing linear regression, you do this with technology, nobody does this by hand anymore, is it finds a line such that all of these distances are minimized, right? So these little dots represent actual observed points in your data set. And then this line is the line that minimizes the error. So the vertical distance from the line to the point is the error, because for this value of x, the line says we should get this value of y, but in fact we observed this value of y. And again, for this x, the line gives us that height, but we actually observed that height, and so on and so forth. So it's always going to try and minimize those errors, and that's what linear regression does. It gives you what's called a line of best fit. So that brings us to this idea of modeling, where we're going to create an equation, a mathematical model that is going to hopefully provide us with a similar pattern as the data that we've seen, so that we can predict, right? Based on this, we can now kind of expand our model outward and predict what kind of outcomes we will see in the future, or with, different inputs depending on what your X value represents. And as I said, they don't always have to be linear, right? We could use quadratic or any power, cubics, quartic, and so on and so forth. We could do logarithmic, exponential. You could use trig functions. I mean, anything. It just depends on what fits it best. Now, there are, really complicated formulas to do this by hand. Nobody really does that anymore. Instead, you use some sort of technology. Even the TI graphing calculators are pretty good at this, but if you're really doing it for real, with some tough stuff, you want to use some fancy software like R or SAS or even SPSS, things like that. Some data sets just have no pattern, so they can't be modeled, right? And then some modeling provides a formula that relates the data. Even though the model itself may accurately fit the data set, it still may not be a good predictor for values outside of the data set. So, you collected data, let's say, on household incomes, and you took data based on household incomes versus years of school, right? So how many years people went to school. And you calculated a bunch of data. You collected a bunch of data, and you get a plot, and you find a certain function that fits your data fairly well. But the problem is, maybe you only collected data for people that had anywhere from a high school degree up through a bachelor's degree. And then you fit this function to it, and it fits really well. And then you go, okay, well, now I can use this to predict how much money people will make if they have a master's degree or a doctorate, right? Or if they don't even have a high school degree, so, going on the low end. But you might find out that those relationships change drastically, and they no longer fit that same function that you use to model basically the middle of your data. So just keep that in mind, that even if you fit your data well, it still might not predict at the extremes, right? If you expand out the window and look at get a wider shot, it might not fit anymore. So here's some basic graphing of dots and then trying to fit a pattern to it. You can see that this one would fit a quadratic pretty easily. This one would fit a cubic, right? A power of 3 is going to give you a shape like that. This one's obviously fairly linear. So the idea is from the shape of the scatter plot, you would then try and fit the appropriate curve to it. Now, if you want to do this with a graphing calculator, it's not too difficult. You just have to put your x values into list 1, your y values into list 2, turn on your plot, and go from there. There's all sorts of videos out there that will show you how to do things in the TI. I don't want to spend a lot of time here because this is really just a general talk about thinking about it in generality and not using any specific type of things. So another example might be if we look at the following table, it gives the amount of tax paid per capita per person for selected years from 95 to 2008. We can create a scatter plot with X representing the year 1990. So 95 would be 5, right? And so on and so forth. The reason why we would start at 1990 is it just makes the numbers more intuitive, right? If we started at 95, then the year 1996 would be X equals 1. It makes more sense to start with X representing 1990, so therefore 1995 equals 5 and 1996 equals 6, right? So it just makes it a little bit more intuitive when you're looking at the graph. And so let's see if we can find a cubic model that fits it, graph the function, and then use it to predict. Here's the data. Here's the scatter plot. You can see that it kind of looks like an upside down parabola, but not really well. So that's why we're going to try and fit a cubic to it to see if we can get, because a cubic kind of has this lightning bolt effect. So you would go into your calculator and you would do cubic regression on the data points, and it would come back, at least the TI would come back with this formula. Then if you graph that formula along with the data values, you can see that it fits really well. And then based on that, of course, you can predict, and it's really easy to predict because you just go into the table function, and if you change the settings to ask instead of autofill, then it just leaves it blank, and then you type in the value of X, and it gives you the corresponding Y. So if we wanted to find out the per capita in 2020, remember that X equals 0 was 1990, so that's 30 years on, so we put a 30 in there, and then this is what it tells us the prediction would be, 14,982 per person. Okay, so that's just the basic generic idea of trying to fit a function to your data points.